Okay, welcome to Math 150, Section 1, 2021, Lecture 1. Today there was a request to do an integration problem, so we will do that first, and then we will turn to doing sequences and series. I will put some instructions on the exam over here. If anybody wants to take a photo of that, just send that to me. I will then just email that to everybody else later. Okay, so the question was finding bounds to integration. How do you want to do it? So this is one of the problems from the book. We have the line y equals x, and we have the parabola y equals x squared minus 2x. So the first thing when you have something like this is to draw what's going on. The line y equals x is pretty easy to draw. And then what we want to do is we want to see where does the parabola hit the line. Well, one point is going to be very nice. When x equals 0, I know this is going to be 0. Actually, I can look at this and I can see the second root of this parabola. What's the second root? 2. This is just the same as x times x minus 2. So the roots are 0 and 2. And so in fact, if this is 0, if this is 2, then the vertex is going to be all the way down here. It'll look something like this. How would I find where the two curves fit? Yeah, so you can show. So I want x equals x squared minus 2x. So 3x equals x squared. So hit at x equals 0 and 3. And so it looks like my picture is actually a reasonable picture. So there are two ways to integrate this. We can first do things, fix an x and then go vertically, or we could fix a y and go horizontally. One way is going to be better than the other. Which way do you think is going to be better? Doing the horizontal integral first or doing the vertical integral first? Vertical, why? Yes, the bottom curve is always the bottom curve if I'm going up like this. If I'm going in the other direction over here, it goes from line to parabola, and from here, it goes from parabola to parabola. It is much better in life to do many easy problems than one hard problem. And so let's do first the vertical integration first. That's going to be the nicest one. So what's my range for x? X goes from what to what? 0 to 3. So x goes from 0 to 3. And then y goes from the bottom curve, the lower curve, as a function of x, to the upper curve as a function of x. And then just integrate the function 1 dy dx. So I have to figure out what are the upper and the lower curves. Well, we're very fortunate that we're given y as a function of x. So if I want to write down here, what's my lower curve, and I want y to be some function of x, what's that function of x? It's just x squared minus 2x. And for the upper one, y equals upper of x, it would just be x. So the way things are presented, everything's presented beautifully for something like this. And this would just be the integral x goes from 0 to 3, integral y goes from x squared minus 2x to x, 1 dy dx. Okay, so if I'm trying to do the integration, I would now get the integral x goes from 0 to 3. The y integral is easy. What is the antiderivative of 1 with respect to y? Y. So I'll do it really explicitly. It's y evaluating x squared minus 2x as the lower bound and x as the upper bound dx. Well, this is the same as the integral x goes from 0 to 3 of x minus x squared minus 2x dx. Is that correct?
Why is one instead of like the first to bottom?
So I'm just integrating the function 1. That's the function I chose to integrate. If I integrate this function, this is basically going to be giving me these heights. So if you want to find the area under the curve, one way to integrate the area under the curve is to integrate the function 1 over the entire, the area of the surface. One way to find the area of the surface is to just integrate the function 1 as your integrand over the region. I could do this as an x integral to find the area. I could say the area is the integral x goes from 0 to 3 of, say, the height at x dx. And this height would be y top of x minus y bottom of x. And that's the same as the integral from y bottom of x to y top of x of 1 dy. They're all ways of writing the same thing. And so if I want to write an area, I can actually view the area as a one-dimensional integral. Or I can view it as a two-dimensional integral where the integrand is 1. So is everything okay going from here to here? Okay, what did I do wrong? It should be plus 2x. I have y at x minus y at x squared minus 2x. There should be parentheses around this. And then to be extremely pedantic, I put the brackets like this so I know what the dx is going by. Very easy to drop a minus. So this is then just the integral x goes from 0 to 3. We'll have x minus x squared minus 2x becomes a plus 2x. It's going to become 3x minus x squared dx. This is now a Calc 1 integral. So now we'll have 3x squared over 2 at 0 and 3 minus x cubed over 3 at 0 and 3. And so I'll get 27 halves minus 27 thirds would be 27 sixths. When you do the algebra. And if I reduce, 3 goes into that 9, and 2 goes into that 2, which does equal the answer as well. Notice that when I was substituting in 3, I didn't have the x cubed over 3 just become 9, because I knew I had a 27 here already. I'd rather keep them both as 27s and just subtract the part. It doesn't really matter how you do the algebra. Okay, so that's the nice way to do this problem. The other way like this, I'm going to have to now break it into two different integrals. And so I'll have, be very careful. So when I look at this, I'm now going to fix the value of y. What's the lowest value of y? So we know this is the point 0, this is the point 2, not drawn to scale, that's the point 3, this is the point 1 over here. So when x is 1, if you look at the parabola, y is negative 1. So this would be negative 1 over here. Does everybody see how we find the vertex of the parabola? We know the two roots are 0 and 2, so the vertex is right halfway between them. What about the highest point? How high do things get? Well, we go all the way up to x equals 3, so when x equals 3, what does y equal? 3. So we would have the integral y goes from -1 to 0, and we would have the integral y goes from 0 to 3. And now we just have to figure out what is the x range for both. And so now for this one, I'm going from one part of the parabola to the other. All right? So how do we figure out where we're going from? We have y equals x squared minus 2x. So we want to figure out how to write x as a function of y. How would you do this? Yes. Good. The other way is to do the quadratic formula, but it's much better to add 1, because if we add 1, then we have x minus 2x plus 1, that's a perfect square. And the algebra will be easier. You can use the quadratic formula, and the quadratic formula will give you the two different roots. That's going to work very nicely for this as well. But I could do it as, y plus 1 is x squared minus 2x plus 1 is x minus 1 squared. So now I get x minus 1 is plus or minus the square root of y plus 1. So x is 1 plus or minus the square root of y plus 1. If you use the quadratic formula directly, you would also get this. So it doesn't really matter which way you do it. If you are able to see the adding 1, that's a nice trick. So I would then have this, which is going to be the bottom, which is going to be the left, the negative or the positive? The negative. So it would be x equals 1 minus the square root of y plus 1 to 1 plus the square root of y plus 1 dx dy. And now for the other one, I have to figure out what x is as a function of y. Well, I already know that on this part of the parabola over here, it's the plus sign. So over here, this is going to be x equals the square root of y plus of 1 plus y plus 1. Now, I have to take the function y equals x, and I have to rewrite that as x as a function of y. All right, if I tell you y equals x, what would x be as a function of y? Yeah, x would just be y. So that's actually pretty easy to rewrite. So here, the x goes from y to 1 plus the square root of y of 1 dx dy. Is anybody excited about integrating this? No. And this just shows you that for a lot of problems, sometimes one way is better than another. So by going horizontally, first, we have two issues. First issue is we have to break it into two different regions. Second issue is we have square roots. So it's not going to be nearly as pleasant. But what should happen at the end of the day? It should be the same answer. So even though it's not pleasant, it provides a good way to estimate what's going on. And you can do lots of calculations to see if this answer is reasonable. I could say, well, I could look at the triangle like this and say that maybe the area I'm adding here is more than the area here, and just approximate this by base 3, height 3, 9/2. And basically say maybe that little cap seems maybe similar to this, which interestingly is the right answer. So as a rough estimate, 9/2 is not bad. So the answer looks plausible like this. Okay. Any other questions before we move to sequences and series? So as you saw in the video, sadly, in other years, I would bring in the basketball net and people would shoot. With all the stuff that's going on this year, I don't think that's permissible, unfortunately. So what we'll do is we're going to talk about some key sequences and series. It turns out that the most important series is the geometric series. And the reason is it's easy to understand. And it turns out we can convert a lot of analysis to looking at the geometric series. The best way to think about how we're going to deal with sequences and series is to think about how you find roots of a quadratic. So if I give you a general quadratic, what's the first thing you try in terms of trying to find the roots? Factor. So if I give you x squared minus 7x plus 12, can you look at that and see the roots? So what would the roots be? So the x minus 4, x minus 3, so the roots are 3 and 4. So for some parabolas, if you can just look at it quickly and see the roots, then you can just factor it. It's a little bit of an art form to just see how to break up the numbers in my mind. Worst case, you can start going through the possibilities. Well, I can write 12 as 1 times 12, as 2 times 6, as 3 times 4. And that will give me the different possibilities. And so, because it's the negative 7 here, and this is a positive, the signs have to both be negative. And so it's either x minus 1, x minus 12, x minus 2, x minus 6, x minus 3, x minus 4. As your number has more and more factorizations, it gets to the point where if you can't just see it, it's going to be faster to just use the quadratic formula. But at the end of the day, if you're stuck on a quadratic, can I write down a quadratic that you can't find the roots to? If I really wanted to, could I write down a terrible quadratic, which would be beyond your ability to find the roots? No. What can you always use? Quadratic formula. No matter how hard I try, I can't stop you. So you can always go back to the quadratic formula. You have that in strategic reserve. When we're doing sequences and series, the first question you always ask about a sequence or a series is, does it converge? And so a sequence will be, A1, A2, A3, blah, 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 blah. These will be the terms in the sequence. Sometimes we start at A0, sometimes we don't, doesn't really matter. We talk about the partial sums, and that would be Sn is A1 plus An, or in summation notation, it's the sum, so it goes from 0, it goes from 1 to n of AK. And then we often look at the sum, which would be the limit as n goes to infinity of Sn. And it's not always the case that the sum converges. But in many cases, as you keep adding more and more terms, the result stabilizes. The geometric series is very easy to analyze, and it turns out you can study most series, or a lot of series, by comparing them to the geometric series. So if you understand what the geometric series is doing, you often understand what other sequences and series are doing. So there's a lot of different results you can prove about sequences and series. So a lot of them are intuitive. If I tell you a sum converges, what does that mean in your mind when you hear a sum converges to 8? If I tell you this sum converges to 8, what does that mean?
Adding up numbers will end up in 8.
Okay. So as you add more numbers, you will. So will you eventually get 8 if you add enough numbers?
I'm not sure. Some will the limit? I don't know.
Well, so this is why you've got to say, what does it mean for the limit to equal 8? As we add more and more terms, the sum gets closer to 8. And the more terms we add, it should be in a closer and closer and closer neighborhood of 8. If I want to be within 1/10 of 8, there should be some n such that if I have at least this many terms, I'm within 1/10. And you say, actually, I want to be within 1,000. Okay, well, then, if you add at least this many terms, no matter how many terms you add, as long as you've added this many terms in the beginning, you'll be within at least 1,000. I want to be within a billion, 1/1,000,000,000. All right? If you add this many terms from this point onward, you're never going to be off by more than 1/1,000,000,000. So as you add more and more terms, I can have a smaller and smaller and smaller window about 8. And eventually, those partial sums will be in that window. Okay? So this is very similar to our concept of limit before from the function. What does it mean for the limit to exist at a point? It means as x approaches a, f of x approaches f of a. So this means that the limit as n goes to infinity of Sn equals 8 would mean that the limit as n goes to infinity of Sn minus 8 equals 0. So as n gets larger and larger and larger, the distance from 8 is going to have to be going towards 0. So if you want your partial sum to converge, what must be true about the individual ANs? Do we know anything about them if the sum has to converge? Good. So if Sn converges, then An has to go to 0. If An is not going to 0, then that means that you're going to be adding sizable boosts. It is very important to make sure you go both ways and see, are both implications true? If An goes to 0, does Sn converge? So does Sn have to converge if the ANs go to 0? So we know that if you're going to converge, it's necessary that the ANs go to 0. It's not sufficient. Can somebody give me a necessary condition for passing Math 150? Nope. You can pass the class without knowing. Most basic, if you want to get college credit for a course, what should be true about your transcript? You didn't get it. You must be enrolled in the course. Hopefully our system is good enough that you will not be receiving course credit for a class you haven't taken. If you want to pass a course, be enrolled in the course. If you want to win a game, you should be playing in the game. Is playing in the game sufficient to ensure that you win? No. So we want to understand the difference between a necessary and a sufficient condition. This is a necessary condition. It is necessary for An to go to 0 in order for the series to converge. But it may not be sufficient. Any fans of the movie Dodgeball here? If you're a fan of Dodgeball, you can email me without looking up the line in the movie Dodgeball where they talk about, is it necessary? You can come up with lots of interesting examples. It is necessary for the ANs to go to 0, but is it sufficient? If I know that the ANs go to 0, is that enough to know that the series converges? Well, let's look at the following series. 1, 1/2, 1/2, 1/3, 1/3, 1/3, 1/4, 1/4, 1/4, 1/4. What am I doing? What will be next? And how many times will I have 1/5? And after that, what comes next? And notice that some of the 1/2 is 1, some of the 1/3 is 1, some of the 1/4 is 1, some of the 1/5 is 1. What's going to be true about this sum? It diverges. So sum diverges. An goes to 0 is not sufficient. So it's always good to try to come up with some, examples. And here, the terms are clearly tending to 0. And if you give me a number like 1 over a million, I can tell you exactly how long I have to wait before every term is less than 1 in a million. But I have rigged it so that the sum will diverge. So always do the easy things first. So if you're asked, does a series converge? Do the partial sums converge to a number? If the ANs aren't going to 0, is there any need to do anything further? No, you're done. If the ANs are going to 0, however, you have to do more work. Because there are cases where AN can go to 0, but the sum may not diverge. Okay? There's a lot of reasons why we want to study sums. It is very rare to have a nice, perfect closed form expression for something. And you can frequently view a sum as maybe a main term and a series of correction and error terms. Any physics people here? All right. So have you done the fine structure constant? So the fine structure constant is one of the most beautiful constants in all of mathematics. I think it's almost 1 over 137. And for a while, people were fascinated by the fact that it might be the reciprocal of an integer. It is unitless. It is a combination of a bunch of fundamental physical constants, and all the units cancel. And so because the units cancel, it doesn't matter what system you use of measurement. You can use the terrible English system, you can use the metric system, you can use your own system. It's a number that's magnitude has meaning. When I tell you the force of gravity is 9.8 meters per second squared, or if I tell you it's 32 feet per second squared, those are basically the same. I'm just changing between the two units. If I just told you 9.8 versus 32, which one is larger? Well, if I'm not giving you units, 32 bigger than 9.8. But the units you use matter. Depending on how you adjust your units, you can get different answers. In a lot of things in physics, we actually have expansions in terms of the fine structure constant or Planck's constant, and you have the main term, and then you have a series of successive terms. You can often recover classical mechanics by sending Planck's constant to 0. And then that would basically say, the only thing that matters in the series is the constant term. And then quantum mechanics comes in with the subsequent terms. You could be doing something in economics where you're modeling the impact that something is going to have, some policy is going to have on the nation's GDP or tax revenue or something. And you might have the main effect, but then you could have secondary effects. How many people have done economics? So you might have done the multiplier effect for money. Right. Not yet. Okay. So if I give you money to spend, not only do you spend money, but if you spend money on local businesses, then those businesses have more money to spend, which means that they might increase their purchases, which gives more money to those people. And so the effect of spending money is actually magnified. And that's a great example of a geometric series, where you'll have all of these lesser effects, and you want to try to figure out what is going to be the total impact of all of it. Okay. So the first thing we want to understand is the geometric series. It is the most important series to study because it's so easy to use and we can approximate so many things by it. So, the geometric series. So simply 1 r squared r cubed dot 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 dot. I could, of course, multiply every term by a fixed constant, and I would just change the sum by that fixed constant. So if I know that the sum converges to 8, if I multiply every term by 5, the sum would now converge to 5 times 8, or 40. And the first thing you might want to do is you might want to look at the partial sums. So Sn would be 1 plus r squared plus r to the n. The video has a more entertaining way of calculating this by imagining a game between Larry Bird and Magic Johnson. Two of the main basketball players from when I was a kid. The standard way to prove this is a really nice algebra idea, which we've seen before. We've seen it when we've done the proof of the fundamental theorem of calculus, telescoping series. And this fits in very nicely with what we were doing earlier today with double integrals, trying to find a nice way to do the algebra. To some extent, a huge amount of mathematics is all about finding a nice way to view the algebra so that you can see where things are going. If I multiply this by r, 1 times r is r. Where should I write that? Should I write that under the 1? Where should I write r times 1? Under the r. And then r times r is r squared. I'll write it under the r squared. R times r to the n minus 1 is r to the n. And then r times r to the n is r to the n plus 1. And now if I subtract, I get Sn minus r times Sn. We subtract, which is the same as 1 minus r times Sn. And when we subtract, notice that everything cancels except for the first and the last term. So we get it's 1 minus r to the n plus 1. So we get the partial sum Sn, which is the sum that goes from 0 to n of r to the k, is 1 minus r to the n plus 1 over 1 minus r. And I can write that as 1 over 1 minus r to the n plus 1 over 1 minus r. So this would be my sum for a finite geometric series. And now what I want to do is I want to take the limit as n goes to infinity. Well, if I want my sum to converge, what must be true about the individual terms of a sequence if I want to have a chance for the sum to converge? So if I want the infinite sum to converge, what must be true about the individual terms? What must they be doing? They must converge to 0. Is that enough to ensure that it converges? No, but it's a necessary step. And so I need these terms to be going to 0. So what must be true if I want r to the n to be going to 0? What must be true about r? What can you tell me about its size? Less than 1. So if I take I equals negative 50, that's less than 1. Can I do that? All right, so let's refine less than 1. Its absolute value is less than 1. So if the absolute value of r is less than 1, it has a chance of converging. And if you look at what goes on here, as n gets very, very large, does 1 over 1 minus r, does this change with n? No, this is fixed. This part, however, has n dependence, but it's just r to the n plus 1. So if r is less than 1 in absolute value, this part goes to 0. So we get, if the absolute value of r is less than 1, then the limit as n goes to infinity of Sn is 1 over 1 minus r. And so we have a beautiful result for the sum of a geometric series. So we know the infinite sum. Okay. Any questions about the geometric series? So it's always nice to do some examples. Let's take r equals 1/2. So we have 1 plus a half plus a 4 plus an 8 plus a 16 equals 1 over 1 minus 1/2. What's 1 over 1 minus a half? It's just 2. Let's see if this is reasonable. Here's 0, here's 2. The first term, I go from 0 to 1. I've covered half the distance. On the next step, I add 1/2. So I go up to 3/2. I cover half the distance that remains. On the next step, I go 1/4. I cover half the distance that remains. Each step, I cover half the distance. Does anybody know what paradox this is related to? Zeno's paradox. Best excuse I ever had for somebody being late to class was, sorry, Professor Miller, Zeno's paradox was a bitch today. So, Zeno's paradox is you can never travel anywhere because before you get anywhere, you have to get halfway there. And before you get halfway there, you have to get a quarter of the way there. And so on and so on and so on. And so it's quite reasonable that this infinite sum should be 2. As we take more and more terms, we see ourselves getting closer and closer and closer to 2. We're never actually there at any finite moment. But as time passes, we get closer and closer and closer. So for all practical purposes, we're at 2. Let's take another example. Let's take 1 plus 2 plus 4 plus 8 plus 16. And so in this case, what is R? So for this problem, what would R equal? 2. So it's 1 over 1 minus 2, which is -1. So if you sum all the powers of 2, you get -1. It's so large, it goes past positive infinity, comes up from negative infinity, and then runs out of steam at -1. Does this make any sense? No. What did I do wrong? 2 is greater than 1. The absolute value of R is greater than 1. Cannot use. So before you use any theorem, you always want to check and see, are the conditions met? If the conditions are not met, you can't just plug it in and hope for the best. There's a lot of modern physics and number theory that actually makes sense of stuff like this. And so the fact that this is -1 actually makes sense in some advanced algebraic number theory. If you sum all the positive integers, you actually get -112. And that actually does make sense in modern number theory and physics as well. It's fascinating how you deal with that. For us, however, we know what we mean when we're adding all the powers of 2. There is no way a sum of positive numbers should be negative. This is a clear indication that we've done something wrong. So this is how you would use the geometric series. If I asked you to only add a couple of terms, you would use the finite formula. If I multiplied every term by 3, you would just multiply the formula by 3. All right, what I want to do now is I want to give an example of why we have to be careful with interchanging orders of integration. I do not want to give you a function of 2 variables that integrates differently if you do x first and then y, or y first and then x. Instead, I would rather give you an infinite double sum because it's easier for me to just show you the double sum. And then what you can do is you can smear things out and you can make a function from this, but the point is easily made using sums. It's more difficult and more painful to do with integrals, so I'm going to just do it with sums. And so I'm only going to look at a double sequence with non-negative indices. So here, I'm going to start drawing an infinite number of dots. And this goes off to infinity, but I don't have time to do that. So here is a 0, 0, a 1, 0, a 2, 0, and so on. This would be a 0, 1, a 1, 1, a 2, 1. This would be a 0, 2, a 1, 2, a 2, 2, and so on. And I'm going to define the values of these as follows. It's going to be plus 1 here, minus 1 here, and then 0 for the rest of eternity. It's going to be 0, plus 1, minus 1, and then 0 for all eternity. What do you think it's going to be here? 0. Here? Here, -1, and then 0 for all eternity. Let's look and see what happens if you sum vertically. What can you tell me if I sum vertically first about each column? 0. So if I do vertical, then horizontal, what do I get? So each vertical sum is 0. So if I do the vertical sum first and then I sum all of those, what do I get? I'm sorry? I get 0. What if I do horizontal, then vertical? What's this horizontal sum? 1. What's this horizontal sum? This horizontal sum is 0. What's the next horizontal sum? Every other horizontal sum is 0. So if I do the horizontal sums first and then add all the horizontal sums, what do I get? It makes a difference the order at which I add them. Doing vertical then horizontal is not the same as doing horizontal then vertical. And this is why in the Houdini theorem, we needed to have the assumption that the integral of the absolute value is finite. So in Houdini, the integral x integral y equals integral y integral x if the integral of the absolute value is finite. That was the condition we needed to interchange. If we put in absolute values here, what can you tell me about the sum? Yeah, the sum will go to infinity. I have infinitely many plus ones, I have infinitely many minus ones. If I put in absolute values, the sum is clearly going to be infinite. And so it violates this finiteness condition. But this is why we have to be careful. It is not always the case that you can interchange orders. If you are working in a situation where the double integral is finite, then you're okay. And I spent many months as a postdoc, working on a project for a professor where I eventually realized that while he had a really good idea, the approach was fundamentally flawed because it required us to interchange an order of integration, which was not justified. So you always want to check and make sure, can I do this? Can I use this theorem? And this was one of the few cases where you could not. Any questions on what we've seen up till now? Yes?
When you're doing horizontal,
Yep.
why isn't the negative one cancel?
Because in the first row, there is no negative one in that row.
In the top one.
But this goes off to infinity.
Oh, yeah.
Right? Due to lack of time, I haven't gone along. But if you go further, next to it will become a plus one. And that will cancel that. Yep. So this shows you that the subject really does have some issues. All right, so we'll end with the harmonic series. So it's 1, 1/2, 1/3, 1/4, 1/5, and so on. So AN is 1 of them. So it turns out this series diverges. The best way to see this is to use calculus. And not only will you get that it diverges, you'll get some information about how quickly it diverges. It turns out it diverges very slowly. There's a couple of ways to prove that it diverges. I think the simplest is 1 plus a half, plus a third, plus a fourth, plus a fifth, plus a sixth, plus a seventh, plus an eighth, plus a ninth, plus a 16th. So do you agree, if I look at just this term, that this is 1/2? Do you agree that the sum of those terms is greater than a half? Because I have 2 terms, and each term is at least 1/4. On the next one over here, I have 4 terms, and each term is at least 1/8. What can you tell me about that sum? It's greater than a half. Over here, I have 8 terms that's at least 1/16. It's greater than a half. So if I march down like this is enough to prove that the sum diverges. Because I just take larger and larger windows, and with the larger and larger windows, it's going to just be adding at least a half, at least a half, at least a half, at least a half. So the infinite sum diverges. You can actually get an upper bound without too much trouble. You can do it the other way. I can go from, 1/4 to 1/7, and that's going to be, at most 4 times 1/4. And so we can actually estimate this without too much trouble. It goes to infinity, but very, very slowly. And we'll do far more on that later. It's a more interesting way, though, to prove that it diverges. So let's let S be the sum, and goes from 1 to infinity of 1 over n, which is the same as the sum of n odd 1 over n, plus the sum of n even of 1 over n. So this is a nice trick, breaking things into the evens and the odds. So I can write this as a sum. K goes from 0 to infinity, 1 over 2k plus 1. Those are going to be my odds. Plus the sum, k goes from 1 to infinity of 1 over 2k, which is my evens. So I'm just writing an arbitrary even as 2k, an arbitrary odd is 2k plus 1. And I start off with the first odd as 1, 2, 3, 4. Which do you think, if the sum is finite, so we'll assume it's finite, which do you think is larger, the sum over the evens or the sum over the odds, or do you think they're the same? So here we have 1 plus a third plus a fifth. Here we have 1/2 plus a fourth plus a fifth. Do you think the two sums are the same, or do you think one is larger than the other? Yeah, I mean, the odd beats the even shown by 2. 1 beats a half, a third beats a fourth, a fifth beats a sixth. So the odd beats the even. So S odd is greater than S even. So this would be strictly greater than 2 times the sum over the evens. I have the sum of 1 over 2 to the k. What can I do to that sum? I can take the 1/2 out. So whenever you have a sum, if you have a constant term hitting everything, just pull out that constant. Ooh, if I pull out the 1/2 and I have a 2 over here, what happens when the 2 hits the 1/2? Woof, goes away. So this is just the same as 2 over 2, the sum k goes from 1 to infinity of 1 over k, which is just our original sum S. And so we showed if sum is finite, then S is strictly greater than S. Can you be greater than yourself? Contradiction. And so this proves that the sum of the harmonic numbers has to diverge. And there's lots of other proofs you can do of stuff like this. So, it's a really nice argument. We try to break things into even and odds, and what's wonderful is we notice that this is essentially 1/2 times the original sum. You might have seen this in some integration problems. I call it the bring it over method, where you have the same thing on both sides. And sometimes when you're integrating like cosines or sines, You might integrate by parts twice and you get back to what you started with a different coefficient and you move things over, and that allows you to solve for the integral. It's a really nice technique. And so over here, we now have an example of a series that diverges. The harmonic series diverges. The geometric series converges. All right, so this is a good place to stop.